Today, oh, that's better. Today, we're talking about machine learning and AI and LLMs again. But this time, it's personal. We want to take our nifty little chat app and make it know about our content. To do that, we're going to use a thing called RAG. Let's get a sneak peek of what we're building. Like I said, we're going to make our chat app respond with our own content without retraining the model. And as a reminder, we're offline, open source, local only, no API keys, no cloud services. Now, before we dive into the code, let's go over some concepts. Trust me, it's going to be worth it. So what is RAG anyway? While implementing it well can be tricky, the concept itself isn't as hard as it sounds. RAG stands for Retrieval Augmented Generation. It's a technique to augment a call to an LLM with retrieved information to generate better responses. Said another way, RAG is where you inline relevant content from a knowledge store based on the user's prompt and then send that to the LLM. It solves the problem of making an LLM aware of your own content. But what about fine-tuning? Fine-tuning or retraining is where you change a model's functionality through training. It's computationally expensive, but you only have to do it once. In my opinion, it's harder than RAG. RAG, as we mentioned, is where you add context to an LLM call without changing the model itself. This requires additional setup outside of the LLM, but it's fairly easy to do. Keep in mind RAG is performed every time a call is made to the LLM. As a starting point, I'd recommend using RAG. Well, that's all well and good, right? But how do we actually go about this? First, a quick word on vectors, or tensors, or matrices, or whatever. In mathematics, vectors, matrices, and tensors are distinct but related concepts. In programming, though, we can just get away with thinking about vectors, tensors, and matrices as all basically arrays. The secret sauce here is that you can do mathematical operations on these arrays. Right, embeddings, or also known as vector embeddings. It's where you convert content, such as web pages and images, into vector points and embed them into vector space. Then you can do vector operations on these vector points. This is how we're able to operate conceptually as opposed to literally. Cool story, right? I know you want to know how, but hang on just a second, we've only got one more thing to cover. Let's talk about keyword search. Sort of. In simple terms, you break content into tokens and store them in an index. Tokens can be words, parts of words. It all depends on your particular algorithm. Take the phrase, "the happy dog is walking." We might tokenize that as happy, dog, and walk. To search for content, we're just going to look for literal matches with those tokens. Take the phrase walking dog, we might tokenize that as walk, dog. Then we'll look for a literal match, and we can find one with happy dog walk. That gets us our "the happy dog is walking" result. Refer to an algorithm like BM25 for a full implementation. This keyword search approach has a drawback though. We're looking for literal matches, not conceptual. Take the phrase running puppy, we'll tokenize that as run puppy, and then with those tokens, we can't find a match to happy dog walk. There's no results. Sure, we could add synonyms for dog and puppy, and then walk and run, but realistically, that doesn't scale. This takes us back to those vector embeddings. See, with embeddings plus some math, we can get conceptual operation. This is what powers vector search, which is also sometimes referred to as semantic search. Let's look at a simple, really simple, really simple vector search example. Say we have a vector space of cars. On the y-axis, we have age, so that's going to be 0 to 100, with 100 being 100 years old. And then on our x-axis, we have color, and that's just going to be our standard visible light spectrum, Roy G. Biv. Then let's add a point for a green 1961 Jaguar. It might go right about there. And then another point right about there for a purple 2004 Lamborghini. Now, let's say we want to search for yellow 1957 cars, and it kind of ends up around there. We can then do a nearest neighbor lookup, and that gets us the green 1961 Jaguar, even though the Jaguar is neither yellow nor from 1957, but conceptually it's kind of close, right? Mind you, this is kind of a silly example, and it's very, very, very simplified. But hopefully this is getting you a sense of the concepts at play here. Now, with all of that said, let's go over a high-level overview of how we would set this all up. We're going to have a load phase, which is where we're going to load and process our content. Generally, we're going to need to break it into smaller chunks due to the context window. After that, we're going to calculate the embeddings for all of that content. And then lastly, we're going to store it in our vector store along with any other needed metadata. When we're then running our app, we're going to calculate the embeddings for a user's prompt. We're then going to find relevant content in the vector store using vector search, and we're going to inline that relevant content into the LLM prompt call. And that's our high-level overview of how RAG works. Let's go over our toolkit for today. This is, of course, in addition to everything we covered last time. First piece, and the most important, is the vector store. We're going to start with ChromaDB because it's easy to get set up and running, and it's got a simple and intuitive API. After that, we're going to move on to OpenSearch, which is basically Elasticsearch. Don't get me wrong, Elastic's great, but the free version of Elastic just doesn't have the same features that OpenSearch does. The key thing is both Elastic and OpenSearch provide support for vectors, in addition to a full suite of search capabilities. As a side note, we're going to be using dense vector encoding, not sparse. Sparse is actually better for textual content, but it's not as widely supported. So just to get off the ground, we're going to be using dense. Next, we're going to need something to generate the embeddings. We're going to use Infinity Embedding Server. It's easier just to have it self-contained and off to the side in case we need to scale it. Last is LangChain, although only some of the utilities, not the main library. LangChain's a great package, and I actually used it when I was first getting started, but for our purposes, I think it obfuscates the inner workings a little too much. Okay, let's go ahead and dive into some code. We're picking up where we left off last time, so we have a basic chat app with Ollama, and we have it running in Docker. Let's go ahead and fire up the Docker stack, actually, just so we can go over really the gist of what RAG is about. So we're in our project directory, we're starting up our stack, and I think this conceptually is going to make RAG really click. Mind you, the implementation is a little bit more nuanced and complicated than this, but for getting the concept, I think this is going to really clear things up. Okay, so our Ollama container is running. So what we're going to do is invoke a interactive terminal, a chat session, I should say, with our Ollama process. So you can see here, Docker execute chat Ollama run and then the model. So in this case, we're using Tiny Dolphin again. All right, so now we can start sending messages to it. Like I said, without RAG, it has no clue who I am. So I'm going to say, who is Matthew Haynes? It's thinking, and it pulls up something that was from the training data baked into the model. I'm not a singer and songwriter or producer, I'm a coder, so let's try this again. So as we said, RAG is just retrieval augmented generation. So we're gonna retrieve some context. Let's say, hypothetically, we're pulling this from our vector store. So using this context, Matthew Haynes is the best coder and YouTuber ever. using this context to answer, using this context, using only this context, answer this question in one sentence. Who is Matthew Haynes? All right, so what are we doing? We are augmenting our generation, right? We're augmenting it with this retrieved information. So all we're doing is just inlining some relevant information into our prompt. And again, the actual implementation of this is more complicated, but conceptually, this is all RAG is. So if we go ahead and send this off, yeah, there we go. That's more like it. You can see Matthew Haynes is an exceptional software developer who excels in web development. Yeah, so there you go. That's RAG. Go ahead and cut the video, right? Not quite. We got a lot more to go over. So we're going to start by adding ChromaDB. So ChromaDB is a simple vector store. Again, it's really easy to get up and running. And for our first pass, we're going to start with Chroma. So let's go ahead and add it. Okay, let me stop the stack. So a couple changes here. First up is our environment file. So previously we didn't have any conceptions of what Chroma was or anything like that. We need to add some additional variables in here. So, and we're actually going to be adding an embedding server. Right here we have the instance for the Infinity server, which is just, again, a process to generate these embeddings. We've got our config for Chroma, in this case the host name, which is going to correlate to the Docker, and the port as well. And then also some configuration for Infinity. We're going to be using the all-mini LM L6 V2 model. This is a standard choice. It's a nice trade-off between performance and fidelity. This is the model that we're going to be using to generate the embeddings. You need to use the same model for generating the embeddings and also retrieving them. So this model is going to embed our own content, and it's also going to embed the user's prompts. We're going to ignore our content directory. So for the first pass, we're just going to be putting in some simple textual content and saving it to the file system as the source of truth, and then also storing that in the vector DB. In our Docker Compose, we now have a few changes. So we've got the dependency on Chroma and Infinity from our web app container. So you can see here, Chroma is just pulling from ChromaDB. And really that's all there is to it. We're gonna cache some of the data in a volume, and that's pretty much it. Infinity, on the other hand, is a little bit more config, because we want to pass in the model name without hard coding it. We're gonna create a Docker file for that. But broadly speaking, we're spinning up an Infinity container, and we're gonna, push content into it, and it's gonna get our embeddings out. So the Docker file for that is very simple. So we're just passing in the environment variables for the model and the port, and then we're using that in our Docker file, and then we're just spinning it up here. So you can see we're running the Infinity process, passing the port, and passing the model name, which is going to be that one right here. Okay. Then let's take a look at our app directory. So if we take a look at app, a little bit different, we're going to add two new services, the embedding function and our vector store. Embedding function is just a helper class to define some methods. That is what all these other things are going to expect. We're just going to add some routes for adding content. So we can see add document that takes title and body, and then essentially it's going to store it to our vector DB. And then lastly, we've got a refresh. This is just a helper one that regenerates the vector store embeddings. Then we can see in here, we're now depending on the embedding function and the vector store for our LLM client. Because number one, we're going to need to convert prompts in our LLM client to vector embeddings. And then number two, we're going to need to use that to do a similarity lookup in our vector store. So we do need both of these, and we'll just pass those in. And then we've got our standard boilerplate here to be able to construct these objects for the embedding function in the vector store in our Flask context. And that's it for app config. Very simple. We just have a content directory. And again, this is just where we're going to be storing the textual content, kind of like a cache. Then we're also going to config load from the environment Chroma and Infinity. And these are just our environment variables. Next, we've got requirements. So we've added Chroma, we've added LangChain, and we've added unstructured, which is a natural language processing toolkit. So that's it. All of our new packages. We'll take a look at our Svelte component in a second, but first, let's dive into the backend. We have a content directory, and again, this is just going to be simple textual content. This is just a placeholder so that the directory gets tracked in the Git repository. But you know, maybe you want to take a look at this message here. Just maybe. And then we take a look at our services. So embedding, FSUtils, and vector store are all new. Like I said, the embedding function class itself is just a kind of our own helper function that defines some endpoints or methods that we can call. Very simple. We depend on Chroma. We are using the Infinity embeddings from LangChain because they have some stuff wired up for us. And we're just going to provide, again, some methods here. So you can call embedding. It's going to generate the embeddings, embed query, embed documents, and then also a helper function to normalize some text input. So in this case, there was instances where it was being passed a string or an array or a dictionary. And it's just helpful to be able to smooth over those. So you can pass it either. And it'll just generate the embeddings and then return those. FSUtils, nothing too fancy here. It's just some helpers to save our content to the disk and then also figure out a safe file name for it. So take out white spaces, lowercase, all that good stuff. Real magic is in the vector store. So we've got a few dependencies here, UUID, Chroma, LangChain, and our file system utils that we just went over. So we construct the class. We're passing in our Chroma config as well as the embedding function. We are going to use LangChain's directory loader and text splitter. When you're embedding content, because of the context window size, you need to, in most cases, chunk it up. Because if you have a 20,000 token document and your context window is only 8,000 tokens, well, now you've used up all your context window and you're not going to have anything useful. So what this does is it's going to chunk up, specifically this text splitter is going to chunk up our content into smaller bytes. For the demo, we're unlikely to hit that 1,000 character limit, but hopefully you can kind of see where this is coming from. You have long documents, you split them into smaller pieces, generate the embeddings, and then when you're looking for relevant content, you're pulling those chunks as opposed to the whole thing. This directory loader is just a convenience to scan and loop over a directory on the file system. Specifically, we're using text documents and pull those in. Then we are creating a Chroma client. Pretty simple stuff here. Host, port, and allow reset, which is, again, just going to allow us to refresh the index. We have a collection name, and then we have a function that just makes sure that the collection exists. So if it doesn't exist, go ahead and call refresh collection. Otherwise, we are getting the collection from the Chroma client. And then refresh collection, pretty simple stuff here. We're calling reset, which is going to clear out the index, and then create it, and then load the docs from the disk. Load the docs from the disk. We're calling our directory loader. We're splitting those documents with that text splitter, so it's going to chunk it out if applicable. And then we're going to call our load into collection. There, we are just iterating over these document chunks. And then for each of them, we're just going to call Chroma add. So we're going to set a UUID. We're going to pass in any metadata, which in this simple example is just going to be the title. We're going to have our textual content, and then we're going to have our embeddings for that textual content. There's a method here, add document, that does it for just a single document. So this first one is kind of the bootstrap. It's loading all the documents from disk. This one is what we're going to use later to add incremental documents. So we can see same thing. We're given a single document. We're going to save it to the disk like the other ones, and then we're going to load it into the collection. And same process, load it, split it out, and then load it into the collection above here. And then lastly, we have a query function. So this is how we're going to retrieve content given a input. So we're going to first take our input, get the embedding for it, and then we're going to use Chroma to query based on that embedding. So find the max number of documents. In this case, we're defaulting it to 1. So find the relevant documents based on this embedding. So we're not going text to text, we're going embedding to embedding. And that's our vector store. So that takes us to our LLM client, and this should tie it all together. So this is starting to look a little bit different than last time. If we pop in here, we can see we're passing in the embedding function, our vector store. We've got our LLM client, that's the same. We've got our prompt base. So because we're inlining context, we're going to be doing some string operations. So we're going to start with a base prompt. And you can see here, it's a pretty simple one. It's just, you are an assistant for question answering tasks. Use the following pieces of retrieved context to answer the question. If you don't know the answer, just say you don't know. Use 3-sentence maximum to keep answer concise. And that's it. When we call get a response, stream works the same way. We'll go with response. We're going to build out the chat prompt given our input. And this is where all of the magic happens. Everything beyond that is the same as last time. So let's take a look at get chat prompt. So you can see here, our context is the first thing we're doing. So we're going to get the relevant context. So let's go ahead and dive into that. So given a piece of input, we're going to query the vector store with that input, right? So it might be, who is Matthew Haynes? We're going to query the vector store with that. Again, it's going to do the embedding to embedding comparison, which is going to use our vector operations. We're then going to get some relevant documents back. In this case, it might be a document saying that, again, Matthew Haynes is the best coder. And that's the actual result. It's not the answer to the question, who is the best coder? It's just a document that says Matthew Haynes is the best coder. And it was able to find it based on the similarity to the question, who is Matthew Haynes? So we'll get some documents back. In most cases, we're gonna iterate over them. And then all we're doing is just appending the contents of that document from the vector store to our prompt. In this case, we're storing it as context and then returning it as context. So who is Matthew Haynes? That's the query. Vector store is going to find it based on the similarity using that embedding. The document Matthew Haynes is blah, blah, blah. It's going to loop over that. It's going to return the actual content. Matthew Haynes is the best coder. That's our context. Return that. So then we go back up to here, get chat prompt. So our context is Matthew Haynes is blah, blah, blah. And we can see we're doing just a simple string construction here. We've got our prompt base, which is up here. So all of this. Then we're going to have our question, which is who is Matthew Haynes? Then we're going to have our context. Matthew Haynes is ... And then lastly, just answer. And then we go back up to our chat prompt. So that's the prompt. So what we've done is we've taken the base, we've injected relevant context based on the question, we've put the question in there, and then we're just going to send it off to the LLM. And then it's up to our language model to interpret that context and try to formulate an appropriate answer based on it to the question. And that's it. We've got our usual stuff here from before, and that's the inner workings of a very simple RAG setup. So let's go ahead and take a look at our components. So for our components, the only thing we're really changing is just allowing us a way to add documents to our collection. So you can see here, app.svelte, where you've got a new add document form. All we're really doing is adding some utilities to, show or hide it, and then respond to when someone does add a document. So in our case, if we go here, we have that document endpoint that we had in our app.py. So we're calling document, we're gonna pass the body and title to it, it's gonna save it. Pretty simple stuff here, nothing too fancy. And again, we've just got some Svelte stuff that's doing standard component, hiding, showing. It's gonna be right here. Yeah, it's hiding and showing. We can pop into it. So we've got title and body. We've got a dispatcher. We're gonna have a submit event. It's just a form. We can submit it, sends it back up, and that gets submitted. The chat form is gonna have a button to toggle this modal, and our chat messages only have one little change from last time, but it's not actually related to this RAG example specifically. It's going to do better styling of the HTML. So last time we had some margin on the bottom. So all we're doing is just setting this selector. It's a dynamic selector. Because the body contents here gets added after the fact, any selectors we use like this won't apply because they're not there at build. So we have to use this syntax to be able to target it. So all that said, let's go and fire up our stack again and see what we've got. Normally, if you're cloning this repo, you'd have to run npm install, all that good stuff. But for us, we're already ready to go. Okay. Now our web container is spinning up, and we should see the debugger pin any second now. Development server. There we go. All right. Let's take a look. So we do not have any content in here at the moment. So if we look at our content directory, there's nothing in here. So let's take a look. Who is Matthew Haynes? And okay, apparently Tiny Dolphin thinks that Matthew Haynes is from the US Marine Corps. Let's see if we can add something. Matthew Haynes. Haynes is a coder, a YouTuber. He likes teaching people about coding and AI. All right, let's go with that. So we added our document. Now if we go, who is Matthew Haynes? Let's see what Tiny Dolphin comes back with. Tiny Dolphin, again, does like to fill in some details here. So you can see now it's saying is a 30-year-old, quite, YouTube creator, passion for sharing his knowledge, programming and AI. So Tiny Dolphin took some liberties there, but you can see it is pulling back some information. Let's give another example that's a little bit more out there so we can see that it actually is really working. Let's go with cat. Cats like to eat pepperoni pizza, especially with stuffed crust pizza. Especially when the pizza has stuffed crust. Let's try that. And let's see what it says. What do cats like to eat? Yeah, there you go. And again, Tiny Dolphin, performant, in the tokens per second, quality of responses leaves something to be desired. So we'll go ahead and move on. Okay, let's use OpenSearch now. Chrome is great, but we're going to move to OpenSearch so that we can take advantage of both keyword and semantic search at the same time. There's cases where you actually want the literal match, and in general, it seems like using both together, both keyword and semantic search, provides better results. So let's spin up OpenSearch. And we're gonna copy over our diff, and let's take a look. Stack is stopped. Stack is stopped. Quite a few changes. First up is our environment file. So if we take a look here, we can see, copy it over. A few things are different now. For one, we're going to use Phi3 from Microsoft. It's a small model. It's slower on my Intel Mac for sure, but it provides better results, and it's probably about as good as we're gonna get on CPU Intel Mac. We have then gotten rid of our Chroma config, so that's gone. And now we have a bunch of config for OpenSearch. If you're not familiar, OpenSearch is a full stack of tools. So there's the OpenSearch search nodes, and then there's also a admin interface, a dashboard, if you will. So we're just setting our version number because we're going to use this for all of the tools. And then we're going to have the individual config for both the search nodes and our dashboard. Then let's take a look at our Docker file, Docker Compose. Again, Chroma is gone and it's been replaced with OpenSearch. So our web container is now depending on the OpenSearch node. We go down and we can see we've got two services for OpenSearch. We've got our OpenSearch node and we've got our dashboard. There's a lot of config going on here. It's, you can see it in the documentation. This is essentially what they said in the default, so I'm just sticking with it. I won't really go through most of these. It's what I have been using on local, and it's gotten the stack running, and it's good enough for production. There's some specifics with these that you'll want to consider. Don't just copy and paste it. For sure, don't just copy and paste the admin password or anything like that. And the ports, again, as always, you don't want these exposed. But for local, for demo purposes, really the only thing we're going to take a look at is, okay, we're passing in the admin password that's set in our env. We're going to need that. And then also we're caching the data. We've also got the dashboard. And it depends on our search node, so that's something to note. We're caching the data for this as well in a volume, and that's pretty much it. We're doing some health checks just so we can start the services in the right order, and that does it for our Docker Compose. The app file only changes a little bit. All we're really doing is changing our vector store. Because the methods and all that stuff, we're going to keep it largely the same. So none of the other things change. We're just passing in vector store above, but down here, we're going to be passing in some different parameters. We've got hostname, port, we've got our authentication, and then that's contenter and embedding stay the same. These are used by the OpenSearch Python client. Config, pretty similar. We're actually going to get rid of Chroma because that's no longer needed. And we're going to pass in our search environment variables. And that should do it. Requirements, a little bit different as well. Gone is Chroma, and here we're adding OpenSearch, the Python client. Our embedding function, popping over to services, is a little bit different. So you'll notice here that any references to Chroma are gone. We're just relying on the LangChain wrapper for our Infinity server. And again, any references to Chroma are gone. So we're no longer extending the Chroma client embedding function. It's all just us. And aside from that, it's pretty much the same. So embed documents, embed query, normalize text. One thing that we did add, however, is getting the dimensions for our embedding function. This is going to be used by OpenSearch. When you create a vector field, you need to specify the dimension. In this case, I know that this particular model that we're using is 384. Later on, we'll probably want to do this differently and not hard code it, but for now we just have a mapping that says this model is 384, and we just know that we're going to be using that model, so we can look it up in the mapping. We'll take a look now at the vector store. Vector store looks quite a bit different actually, because it's now OpenSearch instead of Chroma. We still are relying on LangChain for document loading and text splitting. We've got our OpenSearch Python client, and we've still got our FS utils. The constructor's a good bit different. Still content directory, still our embedding function gets passed in, still the text and directory loader, text splitter, that's the same. This is where we're getting a little bit different though. We're going to create an OpenSearch client using the config we passed in. We're then going to set some properties for our config. We're going to use an index called chat documents, and then we're going to set some basic settings. You can see here, these are our defaults. So 4 shards, KNN is next nearest neighbor. So that's used for vector searches. And then we can also see here we have a mappings in here, KNN vector. So we're going to be using our embedding function to get the dimensions here and setting this config for our vector store. We've got a helper function that just makes sure that the index exists when we're doing our constructor. And lastly, we have our search pipeline. With Elastic and OpenSearch, when you run a search query, you can run it through pipeline. So there's index pipelines that happen when you add content in, and then there's search pipelines that happen when you retrieve content. In our case, we're going to use a pipeline to blend the results of a keyword search and our vector search. So here we have a normalization processor that's going to take those two and blend them together. And we're biasing roughly 70% in favor of the vector search, with 30% being the keyword search. So that's all this is doing. And again, this is going to get called on the retrieval side. And then we're also going to make sure that that pipeline is stored in our OpenSearch instance. Lastly, we've just got some default options for our search body. So these are the fields we want to bring back, and we don't want to show the source. Okay, ensure index exists. Pretty simple stuff here. Get the index. If you can't get it, call refresh. And then refresh is just going to drop the index and then recreate it and load documents. Pipeline, similar, try to get the pipeline. Right now we're doing that with a HTTP call, but in a later version, the OpenSearch Python client should actually have a method for this. Get the pipeline. If it fails, refresh the pipeline, try to delete the pipeline, and then recreate it. Pretty simple stuff. Loader, I don't think there's really much that we need to dive into. It's going to be very similar to Chroma. The difference here is because we're indexing in OpenSearch, the shape of it's going to be a little bit different. For our own purposes, we're going to say what model we're using for embedding. It's not necessarily required, but I find it helpful just to keep track of that. And then we're also going to have a property for the embeddings. In addition to that, we're going to have our body field, the ID, and all that stuff. The rest of these helper functions are pretty much the same. The main thing here is just the actual saving it to OpenSearch. The rest of this is just loading and iterating, etc., etc. Okay, these are different. We've got some new searching methods. Query is just gonna wrap around our hybrid query. It's just a helper function. Hybrid query is going to first generate our embeddings for our search. We're going to make sure we're running that search pipeline that's going to blend the results. We're going to set the default options on our body. Size is passed in. This is the number of results. And then we're going to run two queries. So this is the body. So we're going to do a hybrid of these two queries. First is simple keyword match, where we're just doing a match on the page content for the search. And then next is going to be a nearest neighbor vector search based on our search embeddings and the number of results we want to bring back. And keep in mind, our search pipeline is what's going to blend these together. Then we are just going to call search on our OpenSearch client. Index, search query is what we constructed there, params, likewise. And then we get the results back. So this is our hybrid, and that's going to be our default. Sometimes in development and testing, there were cases where I wanted to do one or the other. So these are just helper methods where it's one or the other instead of blended. So keyword is just doing keyword, hybrid, or vector is just doing vector. Okay, so that should be the meat of it. Let's take a quick look at the LLM client. There's not much different there. We did a little bit of cleanup here, and we'll take a bit of a look. So the main difference here is we are now storing our prompts in a prompts directory instead of in a text variable. This is just going to make things cleaner as our prompts get more complicated. So for now, we just have a prompt called simple rag, and we're using Jinja, the templating language. So you can see here, it's a little bit easier to grok now. We have our base prompt as before, context and question. So we're just gonna load this from our directory, save it as our prompt template. And then when we actually go to get our prompt template, we're going to use Jinja to render this with passing in the input and the context. After that, it's pretty much the same as before. So let's go ahead and run it, and we should be able to see some new stuff. With our simple example, it's not going to be that much different, but this hybrid search and OpenSearch stack will scale really well. It's going to provide you, again, search capabilities that Chroma currently doesn't support. OpenSearch and Elasticsearch are very mature stacks. So if we wanted to, we could build out regular search, we could have filters, fields, all that good stuff. And as before, this is going to take a little bit, so we'll just give it a second to boot up. Okay, let's check it out. So let's dive into the OpenSearch dashboard. In this case, I have a session, but you can find the creds in the environment file in order to log in. We should have an index. Okay, chat documents, great. There's 2 documents in there from our file system. Let's go ahead and query it. Chat document search. Let's just see what we're working with. So we can see here, this is our chat documents index. We can see we have 2 documents. In this case, the page content, cats like to eat pepperoni pizza, especially when the pizza has stuffed crust. This is where that came from. And we've got our embedding model and we've got the embeddings. So this is the embedding points for the page content. Our next document, if we scroll down, is going to be Matthew Haynes. Same deal. Here's where it came from. And here's the embeddings for it. So this gives you a quick glance at the underlying data structures. And going back, let's try this again. What do cats like to eat? We're also using phi3 here, in addition to OpenSearch as our RAG backend vector store. The generation's going to be a little bit slower, but the quality of the responses should be better. So you can see here the tokens are trickling in, and it says cats enjoy eating pepperoni pizza, particularly if it features stuffed crust. Not too bad, right? How about who is Matthew Haynes? You can see here, Matthew Haynes is a programmer who also runs a YouTube channel where he educates others on coding and artificial intelligence topics. And it's breaching the veil a little bit about the context. We can tweak that a little bit later. But there's no relation between him and cats eating pepperoni pizza. Fun stuff. So now we're using OpenSearch. In this small demo, there's not much of a difference. But if you scale up your content to have thousands of records, and again, there's cases where maybe you do want a literal match in addition to a semantic match. Maybe you have a product that has an actual trademarked name and you want to find that actual product, not something like that product. So our OpenSearch stack is it's going to scale a lot better and provide us better capabilities, and chances are you might be running Elastic or OpenSearch already. Let's do one last thing. Let's do a little bit of code cleanup, and let's also add some citations. This is going to be particularly helpful if you're setting up a workplace chat app and you're referencing policies or things like that. So for example, what's the telework policy? The chat can respond with its answer, and then it can also tell you where it came from so that you can verify for yourself. It's going to be pretty simple. Let's take a look here, close these out. First up is app.py. Only thing changing here is going to be document. So we're going to have an endpoint where we can find the source document and bring back its context. And that's it. Requirements. We were just adding some testing in here. But that's not directly related to this. We'll jump over to our components in a second. We are going to take a look at our services real quick. So we've got a new class here called Data Loader. And what it's responsible for is lightening up some of the code that was in our vector store. So before, our vector store was responsible for loading up the data and chunking it out and then saving it to OpenSearch. We've gone ahead and split out some of that so that the concerns are a little bit better separated. So Data Loader is going to have any of the LangChain stuff that we were relying on, whereas the vector store now just has a dependency on OpenSearch. So same code as before. Data Loader just has those directory and text loaders, character splitters, and again, all we're doing is just having some functions that we can call to retrieve the content from disk. Our vector store is going to rely on that, and it's again just going to clean up some of this. So if we take a look at the data, loader, so there we're calling it a few times, and again it's just kind of cleaning up our code a little bit. Aside from that, our vector store only has one other change, and it's just going to have a method to find document. So this is going to be used when we're retrieving that citation. And it's going to take a search and return the source document. That's it. Then let's take a look at our LLM client, something tiny bit different there. So for one thing, we're going to provide the groundwork for tweaking some of the underlying parameters, temperature, context length, that kind of stuff. For now, we're not going to touch it. We'll just use the defaults. And then we're also going to add in 2 more prompts. So a system and RAG with sources. So system prompt is the fundamental prompt that the LLM will use. In theory, it shouldn't be able to be overridden by the user with subsequent prompts like a general prompt could be. So this is supposed to be kind of baked in, and for our language model calls, it can't get overridden. But it's similar to what we had before. Question answering assistant. If you don't know the answer, say you don't know, keep it concise, keep it professional. Then we are going to use RAG with sources. And that's going to be the gist. So RAG with sources looks similar to the other one, and actually credit to Elasticsearch Labs. I got the inspiration for this from their GitHub repo. The code is not copied over. They're using React, and the structure of their backend's different, and they're using Elasticsearch. So the code isn't the same. I didn't copy over any of the code, but the prompt is actually heavily inspired. So if we take a look at the prompt, use the following passages to answer the user's question. And basically what we're doing is when we retrieve the context from OpenSearch, we're going to use that metadata. So we're going to have the source metadata, so whatever text file it came from, or if you're indexing web page, you'd put the URL there. So whatever the source was, and then whatever the content is, and then answer it that way. So this is just going to loop over those documents and format them like this. The context is a little bit different. The method to get context is a little bit different because we're doing iteration and we're providing an array instead of a string, because then we loop over it in the template. But broadly speaking, that's pretty much the same. And that should do it for our back end. Let's take a look at our front end component. So our app.svelte now has a message source modal. So this is how we're going to display our source citation. It's going to have some tooling to facilitate that. So when we output our chat messages, we're going to have a link to show the source. And that's what the message source modal is going to show. And then that's also where this code to retrieve the source is going to be doing for us. So when we click the source, get the file name, call get source, which is going to be that endpoint where we retrieve it from our OpenSearch, and then it's just going to display it. We're also going to tweak our chat messages a little bit. We're going to output the sources in our chat message, but we're also going to clean them up and do some formatting. We're not just going to be printing them as text. We're going to print them as clickable links. So the chat message is now going to depend on chat message source, which is a new component. We're going to process the body of the chat message a little bit different. If it's going to detect sources from the LLM response, it'll split it out into both the message and the sources. And then down here, if we have any sources, go ahead and render our source component, chat message sources component. And all that's doing here is just looping over them, displaying them as a clickable button link. And when you click that, it's going to retrieve it from OpenSearch and display it in the modal. So that is pretty much the gist. Let's go ahead and fire it up, and we can go ahead and call it. Okay, debugger pin is there. So let's go ahead and restart this. Okay, let's see. What do cats like to eat? We see cats enjoy eating pepperoni pizza, especially when it has stuffed crust. And it is sourced from cats. All right. And if we click that, we should be able to see the source, cats. And then again, in this case, we're using file system, but hopefully you can kind of see the big picture here. Say we're indexing a whole web page or a whole knowledge store. We can scale this up pretty easily, and we could have this link off to the actual source content. You know, again, maybe you have your own workplace knowledge store where you have policies and things like that. So that's RAG, and that's RAG with OpenSearch, and that's RAG with citations. I think for now, that's all I have for you. Thanks again for watching, and we'll see you on the next one.
Fart.
To
Duck.
Fart.
Duck.
Hack.
man, dude.
Fart.
It's no.
Duck.
We want to take our cute little chat app. And they're very similar. Very similar. And they're very similar.
Duck.
Hack.